All right. And then, of course, my dog. So, what we're going to do today is we're going to talk about the final homework. Um, Final homework gives you a bunch of kind of practice problems. So, um, I'm recording this at the moment. I'm going to see if I can share screens and still let you see me. That where. Okay, there it is. All right. Can everybody see both me and the homework sheet? Unfortunately, oh, it does seem text pop up for 1 second. Let's see if I can get a chat window to appear. Ooh, awesome. Chat window to appear and everything. All right, so we get our feedback. Um, you might want to make the window with me and it's slightly larger because that's where I'm going to be solving the problems. But given that my whiteboard is small, I want to be able to have the problem kind of on screen. All right. So we'll start off then. The first problem that's in here checks to see a couple different things. Number one, it sees if you can um, read Verilog. It's not actually the best because this is pretty old text. I took this from a how to enlarge me. Is it, am I in the small thing and the window is big? Is that the problem, CJ? There's, I don't know if on WebEx, I believe there's a setting where you can make me and the page equal in size. DD. All right, did Sebastian's work for everybody? Maybe what I'll do is I'll strategically share because I am actually wondering if when it's doing the recording, if it's going to record me in some ridiculously tiny size. Um, so I'm going to unshare. Does everybody have a copy of the homework on screen for themselves? Maybe that'll be better. I'll have it up for myself because I have to be able to read it. But um, maybe I won't share the whole thing because I do want to make sure the video recording is recording the largest view of me possible. Because I don't really care about me, but I do care about the readability of this. So is the view of me correct? I just noticed there's a mirror setting on here too. I don't want to make sure I'm not writing in mirror. So does the board actually say hi? Awesome. I don't want to be like writing backwards or something. That'd be like confusing as all get up. All right. I'll move the WebEx window over slightly. And then my PDF view slightly smaller so I'm able to see both. Awesome. All right, so the problem on this, like I said, we're trying to see Verilog, make sure that you can read Verilog and everything works well. We've done problems where we have taken existing code and gone to Verilog. So I figured this would be a fairly straightforward, but still would kind of get you some practice with a different way of looking at Verilog problems, how to read them. Like I said, this is actually a fairly old one. I hadn't actually found it when I was digging through some of my stuff back from like, 15 years ago. Um, so let's see. Um, we've got in this one, it's a pretty typical setup though, right? So we've got input wire X. So I know my input is X. There's also an input of clock. I did not put inside here a reset. So it's just designed for a simple one. And the output is Y. And then we've got state and next state are our internal variables. Right? Um, I, so when we kind of consider this drawing setup, we have to take this piece of text and we're going to make a diagram and a state table. So I'm going to start with a diagram. I've got state 2, I've got state 1. I can see because I look at the case statement. So if you look through the code real quickly, the input and the output are mentioned in the header. You can see state and next state are listed as registers. The always at pause edge of clock state gets next state. That's basically building the memory or the flip flops. And we have an always at star, which inside it only has a single case statement. Um, I've got a begin and end around it, not because I need the begin or end, but I did, I will do that sometimes just in case I'm not sure. Easier not to have to remember, ooh, did I do 2? Um, and I wasn't as worried because I was typing, so it's going to be small anyway. Um, at least that's usually how I think about them. So I'm guessing because, like I said, this is an old piece of code. So let's see. I've got inside the case statement a 2, a 1, and a default, which means I've got 3 states. Um, so I'm going to put 2, a 1, and kind of my default, which is probably going to be state 0. But we'll have to take a look and see what comes up from each one of these. There should be nothing that's a 3 on this, um, or 3s get folded in to the default. So I'll just leave it this way because this could be 3 or 0 or both. So the first thing I'm going to take a look at, because it's really easy to do, I'm going to take a look at the outputs. And you'll notice that the outputs are all inside the states. So I immediately know this is a Moore machine because Moore machines, the outputs are totally determinable by the state only. And I can see state 2 has an output Y gets the value of 0. At state 1, Y gets the value of 0. And in the default, Y gets the value of 1. So um, I can put my outputs right on here in classic Moore style just by reading what the case statement gives for the Y values. For the next state, which will determine the arrows, I look at state 2 and I see at state 2 the next state, which is telling me the arrows, will be defined by this kind of interesting notation of curly bracket X comma 1-bit binary 0, close curly brackets. The 1-bit binary 0 specifies only a single bit of 0. That tells me that there are 2 binary bits that are set, and the arrows will be X comma 0 or X0. So if x is equal to 1, right, then I am going to go to 1, 0, which is 2. So I'll get an arrow that looks like this if x is equal to 1. We usually just put the label of the inputs along the arrow itself. So it'll start at 2 and it will go to 1, 0, x 0. And 1, 0 is 2 in binary. So it starts at 2, and when x is equal to 1, it goes to 2. Because remember, it is an x 0. If x is 0, then it's going to go to 0, 0, which is part of my default state. So when x is equal to 0, I'll get 0, 0, because it's x 0 as the state. That completely handles the situation of 2. Does everybody feel good about that first case statement? Yes. Awesome. Then we'll go to 1. So now we go to the 1 colon. We've already taken care of the y, and it tells us that the next state is going to be 1 bit of 0, then followed by x. So I might have kind of the flip situation, 0x. So if x is a 1, I'm going to go to 0, 1. So I'm at 1, and if x is a 1, I go to 0, 1. So if x is 1, I'm going to 0, 1. It's both my start and my finish. If my x is a 0, then I'm going to go to 0, 0. So if I start at 1 and the input is a 0, I go to 0. So that gives me both of my arrows from state 1. We feel good about state 1 inside of the case statement. Awesome. Okay, then we go to default. Now, remember, default has this question colon, right? Question, and then 2 colon 1. So this notation is going to let one of my 2 outputs through, depending on what the state of x is. So if x is a 1, it lets the first one through. Because this is saying x, is it true? So maybe I should be better labeled here. If x is 1, then you give this output. All right, so this is the true. X is a 1 or true. If x is a 0 or false, it does the second one. So when x, if I'm at this default case and I get a 1, I will go to state 2. And if I'm at a 0, I will go to state 1. That's all that's telling me, right? The real, question colons always look weird, but once you get used to them, they're very, very nice. So it just tells me which way I'm going based on whatever x's value. X is a 1, it does the first. X is a 0, it does the second. That's all there is to it. So, and next state gets that value. All right, does everybody feel comfortable with the default? Okay. In this, there is no requirement for the default case to be anything other than 0. But technically speaking, it could be both 0 or 3. But it looks like 0 is the main one, and then 3 was made to look just exactly like 0, which is a pretty typical case when you have an extra state. You make that extra state that's completely unneeded look just like, the kind of standard case you want to deal with. So this part right here, would be the answer to A. All right. Make a state diagram. Boom. There's your state diagram for this. Making a state table is also nice and straightforward. Um, so I'm going to use this diagram to help me make my state table. So a state table, you have your current state, and then you usually have, where does it go to if x is equal to 0 and if x is equal to 1, and then we usually have our output. So my current state in here could be my default, which is 0, 0, or 1, 1, either of those. And then I've got, if my current state is a 0, 1, and if my current state is a 1, 0, which is 2. All right. I'll just continue this line across straight, and I'll do one line for each to keep them nice and separate. All right, so now all I have to do is walk to each of these states. I'm going to fill the output in first because it's really easy. The default has an output of 1, and the other two have outputs of 0. The output part is done. Nice and easy. I can go to default and I look at where it's 2 arrows, right? At default, the arrow that goes away from it that's labeled 0 goes to state 1. So if the input is 0, the next state will be 1. If the input is a 1, that's this arrow, its next state will be 2. Easy enough. If my current state is 1, which is 0, 1, on a 0, it goes back to my default case. In particular, though, I calculated it by double 0. And if it is a 1, it goes to 0, 1. If I'm in 1, 0, state 2, and I get a 0, that's this arrow, my next state was 0, 0. And if I got a 1, my next state was 1. Boom. That is the answer to B. Right? You could repeat this line twice, once for 0, 0 and once for 1, 1 if you wanted. But you don't have to because it is really the default case. As long as you let me know both of them are good, that's perfect. If you just do default, I'm totally fine with that too. If you say 0, 0, I'll probably take it. There is a little bit of ambiguity on it because what do you do with the 1, 1? But I would still take 0, 0 on there because that is the likely first case. Technically, the original code does actually have both of them carried into it, but 0, 0 is the one it wants. So I would accept any of that stuff. We feel good with the state table. I see one feels good, another yes. So that's all I was asking you to do on problem 1. That makes problem 1 finished. Okay, click over to my PDF. I'm going to just briefly share just so everybody can see. All right, hopefully you can see the second page of the test, in which case I gave you a state diagram. I'm gonna erase this one. Maybe, where did I put my, there's my eraser. All right. So problem 1 done. Problem 2. We're taking a look at this diagram, and the first thing it asks if this is a Moore or a Mealy machine. So it's a state diagram. We actually don't do any
Dr. Schubert,
manipulation. Yes?
So is the out the current out and not the next state out for question one?
Um, so outputs are always where you're at, um,
Mhm.
because next state hasn't happened yet. And
Gotcha.
technically, when you get to next state, it's then the current state. So when we're doing outputs, we always deal with what is my current state and my current input. Next state is telling you where you're going to go in the future, but you don't need to handle the outputs. You'll figure out the outputs when you get there. So you're always working with the current state, current input. A Moore machine only cares about the current state. A Mealy machine cares about the current state and the current input. But outputs only care about the current stuff, not about the future.
Gotcha.
When the
That makes
future
sense.
does come, it'll be current, and again, it'll be handled in the same way. So that reduces the complexity as much as possible. And remember, the person is only seeing the current thing. They can't see the future.
Gotcha. That makes sense. Thank you.
Awesome. That's a great question. Yeah, if you have questions like that, just kind of, interject. I'll see. Uh,
Dr. Schubert, you muted yourself.
Can you hear me now? Okay, I think what just happened is evidently my headphones died.
I can hear you, but I can't see you anymore. I don't know if that's my computer or
Can you see me now? Hello, hello. No, nobody can.
I can hear you now. I can't see.
Oh, weird. Okay, can you see me now?
Yes.
Well, that's so weird. I changed my headphones off and it turned my video off. WebEx is like the weirdest beast on this planet. Could you hear me the whole time?
No.
No.
I can hear you after
I hate WebEx.
table and stuff.
Okay, I'm gonna quickly. I redrew the picture. Let me just try to explain.
I heard you for part 1, questions 1, the whole time.
Part question 1.
No.
Okay, so everybody heard all of question 1.
Yes. It was just when we started not being able to hear you is when the video cut.
It's so weird. Okay. Well, I believe maybe I'm falsely blaming my headset. Maybe there's just something weird going on with Cisco WebEx. I redrew the diagram. This should be, aside from my own messiness, this should be exactly what you have for problem 2. It's got A, B, and C. A has an output of 0, B has an output of 1, C has an output of 0. And you can see A has a 1 going to B. On a 0, it goes to C. C on a 0 goes to A, and to B on a 1. And B stays at itself on 1. And on a 0, it goes to C. Right? So that should be a reproduction of the diagram that you were given. And the first question, A, was, is this mealy or more? And my comment is for more, it happens inside the states. So since the output, the part after the slash, is inside the states, then by definition, it's a more. If the output was on these input lines, that it was like slash and then the 0 was here, then it would be a mealy. On the input, so the slash appears on the arrows, which is where the inputs are. More is always with the states, so it's inside the state after whatever the state name is. Does that feel good? Awesome. That's really the big part. So, asking the mealy or more difference is a, designed to be a pretty quick, easy gimme. You can just look at that and tell. Okay, we have to turn this into a state diagram. I wish I had drawn that slightly smaller, but we might. I'm going to just keep the ABCs on here because I think we can fit it in. And then we have to do a JK flip-flop. Okay. Well, let me see if I can do part B, the state table, down on the bottom. There's probably enough room. Okay. So when we're doing the state table, we need to know what is my current state, and we do our next state. And our next state is going to be dependent upon the input. So I'll put x equals 0 and x equals 1 as 2 different columns. And then we'll have our output. In our current state, I've got A, B, C, and nothing else matters because I haven't specified anything. So that's kind of up for grabs. Now, when I go to do, I'm going to do the state transitions just with the names. When we go to do a design, we're going to have to pick a numbering system, but I don't have to do that yet. So making the state table is just as simple. So if your current state, this part here is the next state, you should always put the inputs going across this way in order because it'll make it a little bit easier when you go to actually do a design implementation. And I usually put the outputs way off to the side because usually outputs are very simple to calculate. All right. So I'm going to go through and fill the outputs in, right? A is 0, B is 1, C is 0. So 0, 1, 0. Output's done.
Next states. I'm going to start with A. If it's a 0, it goes to C. And A on a 1 goes to B. If I'm at B and I get a 1, I stay at B. And on a 0, I go to C. If I'm at C, I get a 0, I go to A. And if I'm at C and I get a 1, I go to B. So in every case, I go to B when X is equal to a 1. All right. So this right here is my state table. And this is really kind of the most basic flavor I need to reduce this to a state table here. So this is totally acceptable as a state table. You could also give me, you could pick a number scheme for each of these and give me that. I would accept that too, as long as I can just tell which one's which. Right. So this is B. Does everybody feel good with B? Awesome. Now we have to do C. To do C, in which case we're asked to do an actual implementation. And it tells us we have JK flip-flops, and then we have to draw this. Right? When I have JK flip-flops, pretty much always tells you you're going to be using the excitation tables for JK flip-flops. And that's, I looked it up in the book because I know some people are having some challenge finding them. The table for JK flip-flops is on page 309. So in the book, it's on page 309. And so we're going to use that table. We don't need this picture at all. We just need this. And we're going to be doing, in addition, a bunch of K-maps. Because when you're doing excitation tables, you're going to K-maps. Go to a Carnot map. I'm going to pick values for these. So I'm going to do A is 0, 0, and B is 0, 1. And I'm going to set C to be 1, 1. I'm going to do it in gray code. Now, could you have done it in regular binary? Absolutely, you could do it in regular binary. Nothing illegal about it. It didn't tell me which one to do. You could do one hot if it made you happy. So why do I pick this? Well, I'm picking this particular ordering here because when I go to make Carnot maps off of this, this is going to be a very easy way to do it because they're already in the right order for it. That's really my whole reason. I'm just being lazy. So that means I come in here in every place, I'm going to replace them. C is equal to 1, 1. B is equal to 1, 1. B is equal to 0, 1. B is equal to 0, 1. And then A is equal to 0, 0. Right. Do we feel good with this so far? So all we're doing now, I don't have to deal with ABCs anymore. I've got specific numbers. So the whole trick is you're given some diagram, you want to implement it. It's easiest to do at a table. Get the specific values in the table. Now I've got to do a design for this. And I'm going to put, where'd be a good spot? Maybe I'll sneak it down here. If you look at the excitation table, pull the book in just so I can kind of show it to you, and then I'll draw a small version of it. Can everybody at least see the book or have access to the book? They're readable. Okay. If you look at this one that says excitation table, you see there's QT and QT plus 1, I believe is how they did it. So you got QT and QT plus 1. Oh, bless you, Megan. Sending a pic to the group. So you have QT and QT plus 1. What that is, the first column is saying the current state, and the next one is saying next state. What you're going to do is you're going to match the current and the next state, and it tells you what the JK input has to be to make that happen. That's the whole purpose of an excitation table. It just tells you if you have, this is your current and this is your next, here's J and K to make that happen. That's a design decision. I know my current bit, right? The least significant bit here is a 0, and it goes to a 1, so I know it's going to be a 0-1 transition. So you've got some possibilities. Current could be 0, next could be 0. Current could be 0, next could be 1. Current could be 1, next could be 0. Current could be 1, next could be 1. And for the JK flip-flops, this is what makes JK flip-flops very nice. You've got a lot of X's. In particular, the X's kind of make this pattern. When the current state starts at a 0 as a bit, K doesn't matter. You can pick any value for K and it works. When the current state starts at a 1, J doesn't matter. Right? You can deal with that. And then the remaining ones follow an XOR, 0, 1, 1, 0. So even though I can't read that table over there, I know this is the pattern, and that's how I remember it. So if you're ever stuck without it, that's kind of the easy way to get it. Now what we have to do, I'm going to try to color code this to make it a little easier. When we're dealing with this, I've got 2 bits in the current and the next state. So I'm going to replace, this is the most significant bit, this is the least. I'm going to replace the least significant bit. Does the purple stand out both as readable but recognizably different? What do the C and N correspond to again? So you've got your current state is where you're at, and next state are the values inside the table. Tells you where you go. Color does not stand out. Let me try a different color then. Is the red readable and stands out? Yes. Okay. So in the I think that should be a 0, shouldn't it? Yeah, that's A. So this should be exactly what it was before, just with red for the second number. Does that make sense? Okay, I'm seeing yes. All right. Question about least and most significant bit. If you were to write a number, let's say the number 7, right? 0, 1, 1, 1. The most significant bit is the largest number. So that's my most significant bit. We just write MSB. And this would be the least significant bit, right? Which is this bar 1. So very often when we're looking at multiple digits, we'll often call them by the most significant bit, the number that's the biggest value, and the least significant bit. So in decimal, like if I was doing 25, the 2 is the most significant, and the 5 is the least significant. So it's kind of relative to your system, but it's always which one is the biggest, is the most, and that's, we pretty much almost always write it on the left. At least in Western languages. And so if you're, that's kind of been dominating the engineering world. So that's where we put them. So when I'm referring to the most significant bit in the current state, I have that as blue, and the least significant bit is red. And I'm about to change that for all the others too. I just want to make sure I got a distinct looking color. This most and least significant bit makes sense? Yes. Okay. That's just a naming convention. You didn't actually need to know that. You just need to separate the two out because I'm basically going to have the left bit, right, is changing from a 0 to a 1. So I'm just doing most and least yes. And so the pattern on the right here is 1, 1, 0. And here it's all ones. Right. So the blue bit transitions to the blue bits, the red bits transition to the red bits. So these are the current states, and these are the next states. So when I'm doing these JK flip-flops, I have to do one for the blues and one for the reds. Is that good? Awesome. I'm going to do the blues, or the most significant bit, first. Since we also, if you remember when we're doing this inside Verilog, we sometimes number them like this. It would be like 1 to 0. That means the left one is bit 1, and the right one is bit 0. So we will often sometimes use 1 and 0 as the label. That's how I'm going to label my J's. This will be J1, which means the J for the most significant bit. And I will have K1, which is going to be the K for the most significant bit. And I'm doing it in the blue pen so that you know I'm only right now worried about the most significant bits. We're going to do one for the blues, and we'll do one for the reds, and then we move on. So far, so good. Awesome. All right. Now I've got 3 down, which really means there's a 4th one, which is 1, 0. Right? But it isn't written because it's just all X's. When I make my Carnot maps, I've got this, and I've got the 1, 0 here. So this bit, which covers this side here, that is the most significant bit of my current state. So this is state bit 1. And the middle one, where they're both 1 here, that's the least significant bit. Maybe I'll do this in red just to keep our blue-red convention going. This is state bit 0. That's the order they're in. Right? The most significant bit is true on the bottom, and the least significant bit is true in the middle. And all of the next state stuff goes inside. That exact pattern is going to be maintained for K. J and K have the same basic pattern. And then I've got my input. I guess it doesn't have to be distinguished, but just to follow our lots of color things so it's easy to see them. You can see this is X equals 0 and X equals 1. So that means this column, X is true. This kind of gives you the same format. To turn this table into what looks exactly like Carnot maps. But at the moment, all we're worried about inside is going to be the blues, the most significant bits. I can put my red pen away for the moment. So I am now going to walk through and fill in each of these. I'm going to start with the upper left corner of each. The upper left corner, the blue bit starts at a 0 and changes to a 1. Does that make sense? Set up my table. Now I'm going to start with 0 goes to 1, right? Which is this upper corner. It's a 0 going to a 1. Okay. 0 going to a 1. I now look in my excitation table because the excitation table tells me what to put in J and K. So I'm going from 0 to 1, so I'm right here. 0 currently becomes a 1. 0 currently becomes a 1. Awesome. It's not just good, it's so good. Thanks, Tyler. All right. That means J should get a 1 and K should get an X. J gets a 1 and K gets an X. Okay. So you notice I've now been able to fill in the first one. To get the upper right corner, that's when X is equal. Ooh, I forgot to write the X on the second chart. This is my input X, as opposed to the X in here, which means don't care. All right. So I'm starting at a 0, and I go to a 0 when X is equal to 1. Start at 0, go to 0. So start at 0, go to 0. I am now on this top one. 0 goes to 0. 0 goes to 0. 0 goes to 0. That means 0 don't care. 0 don't care. Good. Awesome. Beautiful. Cool. All right. Let's go to the next line. I want to fill in these two spots. That's right here. My blue value starts at a 0 and it goes to a 1. 0 goes to 1. I'm back on this line. 0 goes to 1 means 1x. Awesome. Cool. All right. To get the upper right of these two boxes, that starts on the 0 line and it goes to a 0. So it's exact duplicate of what I had before. So I'm up here and it's 0x. Starts at 0, goes to 0. Starts at 0, goes to 0. Put a 0x. Yay. I now go to the lower part of the table. I start at a 1. I go to a 0. And that's actually true for both. Right? So these two lines, when both things are 1s, that's this line. S1 is a 1, S0 is a 1 right here. 1, 1. It starts at a 1 and goes to a 0. Starts at a 1, goes to a 0. So both of these two are going to be identical. Starts at a 1, goes to a 0. That's an X1. 1, and that does the same thing. Very good. Do we have to flip? Notice I picked mine to be 1, 1 here. I did not pick it to be 1, 0. I did that because I didn't want to have to flip. So if you picked it to be binary, which is totally legit, I will grade it perfectly because that's a fair pick. Then you would have a 1, 0 here and you would have to flip. I deliberately picked a 1, 1 because I'm lazy and I'm also dyslexic. Actual true story. So as a dyslexic person, and I'm also mildly dysgraphic, I try to do everything I can to make myself not have to do anything that's going to be hard for me to notice. So I picked gray code as my pattern here, so I don't have to do any flips. So That one just makes it easier for me, and I tend to make less mistakes. So I deliberately did that so I wouldn't have to deal with it, just knowing myself. Right? If you picked binary, it would be totally awesome. I will grade you full credit. Nothing wrong with it. And you would have to flip because it would be a 1-0. I see Meg is good with it. Anybody else have questions up till now? Okay. The last state here is this 1-0 state, right? S1 is 1, S0 is 0, but I don't have one. And it doesn't tell me. So since it doesn't tell me, I could do a lot of things. I could make an assumption of what they are, all kinds of things like that. But I could also say, they didn't tell me, so it's all a don't care. I could care less where it goes to. This is not necessarily the most robust thing. However, I can't say it's wrong because I didn't tell you what to do. Therefore, on a test, this makes your life easier. So if I'm on a test, I would just say, hey, that last line, you didn't specify. On a test, this is much quicker and easier to design. So I'm going to pick don't care for all those states to make my life easy. If you write that statement to me, and I hadn't told you what to do, so the assumption is correct, which it is here, then I'd be like, awesome, good choice. You could also justify whatever pattern you wanted on it. If you picked a reasonable one, I want it to go to 0 every time or whatever. I'd be okay with that too. You could just say 0 is my reset state or something. That'd be a fair way to go also. All right. But in this case, I'm being lazy. And this gives me a really easy. The encirclement for the K here is just everything. So that means my equation is K1 is equal to 1. It's always true. And when I do my encirclement for J1 is equal to X. So that gives me a really nice, simple implementation. Do we feel good about J and K? Yes. Okay. I'm now going to do J0, the reds. Now, I could do it just below here, but then I'd have no room to draw this thing. So I'm going to erase this, but I'm going to leave the J1, K1 here because that has my formulas that I calculated. And that's the thing I'm going to care about for my circuit purpose. And of course, I dropped that. Let me see. Save myself the trouble. I got my handy dandy eraser here. So I'm just going to erase these. All right. Now I'm going to do the ones for the reds. So I now need more colors again. Since I'm doing the least significant bit, the bit on the right or the red bit, I'm going to draw using red. So I'm going to be calculating J0 and K0, which are the least significant bits. It's going to have the exact same shape because the table hasn't changed. The least significant bit is still the middle one. And state 1 is still the bottom. And X equals 1 is still the right-hand column. So I have now reproduced the exact same chart, except now I'm working with the red one. So everything in here is going to be red. Since we've already made a notation on this, that this last state, 1, 0, which is this bottom one, I'm going to pick don't care. I'm just going to write the don't cares in, because that's true for all of them. I made this decision. maybe I should put. I made that decision for that last line. So the X's, I don't need to worry about it. It just, I don't care what it is, so I don't even need to worry about that table. I've already got X's. And X's are good for design purposes. All right, so I only have to worry about the upper 6 here. All right. Then we come through and we go, okay, I'm starting at 0 and I'm going to 1 in both of these cases. So the first row, both J and K, I'm starting at 0 and I'm going to 1. It's identical. So I can look inside here, starting at 0, going to 1. That's the second line in my excitation table. Currently 0, going to 1. Currently 0, the next is 1. Gives me a 1x. And that's the same thing for the next one. Are we good? Awesome. We are halfway done this table now. All right. For the next two, I'm starting at 1, which means you're at the lower part of the table. I'm going to have you notice some cool things. When I start at a 1, J is equal to X. Right? It doesn't matter what the next state is, J is equal to X. So this is another shortcut that I can do, but I'm starting at 1 for all of these 4. So J is equal to X. K is equal to X on the outsides for S0. Because S0 is equal to 0 here, S0 is equal to 1 here. So I only have to worry about technically the K values for these middle ones. All right. So I'm starting at a 1 and going to a 1 on the upper 2. Right? Start at 1, go to 1, start at 1, go to 1. That means I'm on this lower value. Start at 1, go to 1. So I get X, already did it, 0. That's for both of those. So far, so good? Yes. The bottom line, I'm starting at a 1. And the far one over here, I go to a 1. Well, I already know what that is. It's a 0. Starting at a 1, going to 0. Starting at a 1, going to 0. K is equal to 1. That's a 1. So that's that line. That good. Yes. Now we just do encirclements. So the encirclement over here, I've got 2 1s, everything else is X. So the best encirclement I can do is encircle everything. So J0 is equal to a 1. That's a nice, easy encirclement again. When I go to K0, the best encirclement I can actually do is right there, which is X prime and S1. So when X is false and S1 is true. All the other ones, since I got the zeros in this pattern, it doesn't make sense to include them. So that is the best encirclement I can do. So that is my best equation. Do we feel good with this? I don't need these anymore because all I was trying to do was get these equations. I now have those equations, so I don't need anything else. I can now just draw my circuit. I don't need the excitation table either because I only use the excitation table to fill out those lovely JK K maps. I'm going to draw my circuit just all using a black pen if that's okay with you. And I'll just label them. So I know I have 2 flip-flops. have flip-flop number 1 that has a J and a K input. That's this. And I have flip-flop 0, which has a J and a K input. That's described by these. I'm going to do the easy things. The K input for number 1 is equal to 1. Right? You can also do that as power if you want. Typical way we show power is to just put that and run down. J0 is also, J0 also gets a 1 or power. You can either put a little line with 1s, or you could put, connect to the power line, whichever one makes you happy. But I've now done these 2 right here. I need to have X, which is my input, and I'm going to use the inverted one for both of them. So I've got X comes into an inverter. That's all I need for J1. Right. For K0, I need this signal, and I have to AND it with S1. So my state output for 1, this is my state output for 0. So S1 comes around there, ANDed together, and it goes into K. So now this one knotted does that, and this AND gate taking X naught and S1 does this. All that stuff's implemented. The only thing I haven't implemented is my output. And I haven't implemented my output because the output is really easy to do. If you look on this, right? So I can decide what do I want to pick for this. Now I'm going to pick this to be a 0 because it just makes my life nice and easy. And then that means I only get a 1 when the current state, the most significant bit, the 1 side is a 0. So when the most significant bit, S1, is a 0, that's here. And the least significant bit has to be a 1. So I'm at 0, 1. Both of these have to be true, and then my output is a 1. I forget what I called the output. I don't know if I called it. Did I say? No, I didn't. I'm just going to call this Y for output because I think that's what we had done before. Is there a way we should? Which is standard? I've actually seen both. So I will perfectly accept either this, where you see kind of the power symbol coming in, or if you put a 1. So the way I would myself pick is if the diagram's really ugly, right? There's lots of wires going everywhere. I do the 1 just so I don't have more wires crossing things. If the diagram's pretty clean, I'd probably put the power symbol in, just because I think it looks nice. But I got the final AND gate. Yes. So the final AND gate here, this is the output. So I looked at my output and I had 0, 1, 0, X. Since this is in a already put into a gray code ordering, I could pick this to be a 1 for the output if I did both of these are on, which means I need 0, 1, and 1, 0. So I could do an XOR gate. Or I could do what I did, which is I just marked that off, put that as 0, in which case this is the only 1. So I wanted the most significant bit to be 0 and the least significant bit to be 1. Right? Remember the 1 is the most significant bit. So I wanted that to be a 0, so I negated it. So a 0 would become a 1, and a 1 would become a 0. So, this does right here, this AND gate, the min term is S1 prime and S0. That's S1, you have to prime it to make it a 1, and S0, you leave it alone. So this is S1 prime, and this one here is just S0. So I AND them together, that's this term, that is my output. So I just picked the midterm, basically. I could have picked a 1 here, in which case this would become an XOR. But an XOR is slower, bigger than an AND gate is. So since I don't really need it, why pick a big, slow gate? Pick a small, fast one. Small, fast, cheap. So AND gates are nice and small and cheap. So that's why I picked it. But you could have done either. All right. But this gives you your circuit, which is the answer to 2C. So 2C, you should show me these equations and draw me a picture that looks like this. You feel good? All right. I'm seeing lots of positive stuff. All right. Number 3, modulo 11 counter. Sounds scary, doesn't it? So mod counter is the standard name for it. The book often just calls these counters. I have used the name modulo. It should be in the labs too. But whenever you see modulo counters, modulo n counter or whatever, it takes a remainder. So this is sometimes written as mod n, or in C++, you do %n is division takes a remainder. Same exact thing. So if you're looking at the possible values you could get from calculating some number, modulo n, if that number is some multiple of n, you would get 0. If it was 1 bigger than a multiple of n, you'd get 1, right? If the remainder was 1. You could get a remainder of 2, all the way up to n minus 1. You can't get a remainder n. You would have just increased your quotient, and your remainder would be 0. So the possible values for modulo are 0 up to n minus 1. Does that make sense? Awesome. So if I'm doing a modulo 11 counter, that means I go from 0 to 11 minus 1, which is 10. So a modulo 11 counter counts from 0 to 10. These are the possible values it can take. Since it's a counter, it's going to walk through them in sequence, which means it'll do 0, and then 1, and then 2, and then 3, and then 4, all the way up to 10. And after 10, it'll go back to 0 again. Does that make sense? Earlier on in the video stuff I had mentioned, this makes a ring. Right? 0 goes to 1, goes to 2, all the way around, eventually to 10, which goes to 0. So it makes this kind of big ring. I don't feel like drawing 11 circles, but hopefully you get the idea of what you would get from this. Okay? So this is just a counter, nothing more, nothing less. So the whole counter chapter, I think it's chapter 6 in the book, and the videos from a few weeks ago all of those count. Sorry, it's getting. So this was my question to check that particular spot. I didn't tell you what type of a counter to do, but I did give you a restriction. I told you I wanted to use a parallel load register and 4 8-input muxes. So technically speaking, a mux, so if this makes sense, I'm just going to leave that for you in your mind. A mux, it's coming in an 8-input 0, 1, 2, 3, 4, 5, 6, 7. Takes 3 bits, right? Whatever A, B, C, and passes through. But it's only one wire. So when you get a mux, it switches one wire to one wire. Well, to do a modulo 11 counter, right, in binary, this runs from 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, up to 10, which is 1, 0, 1, 0. I have to have 4 bits. You can't have less than 4 bits for 11. And the reason is if the number of digits in here is more than 8, right? So a modulo 8 counter will fit in 3 bits. Anything bigger than a modulo 8 counter needs more bits than 3. Up to, so 8, the next one will be 16, will be the next power of 2 that comes in. So if you're bigger than 8 but less than 16, you have to count as if you're on 16, which means that your 11, which is between that range, has to be 4 bits. So I give you 4 of these, which I'm just going to show by putting the /4. That means I'm stacking them, and I'm going to treat them in the exact same way. That means I've got 4 bits coming out. Does that make sense? Yes. All right. So I want to look at these and then say, okay, I need to be able to build a design here. Now, the design that I'm going to build on these ones, okay, I need to look at this and say, well, I've only got 3 bits here, but I really need 4. I've got 4 transitioning here. So if we look at what our build is, for the first one, I've got my current state, which we can consider this as my current state. It goes to 1. And 0, 0, 0, 1 goes to 2. I'm going to erase this so I can build my table. It won't take much to do this. Right? But this is just to let you know. I can do each mux independent, or I can loop them together. Let me write out the whole table. Right? So I've got my current and my next. And for a counter, the next is just going to be 1 bigger. Four, so the next is 5. 5, so the next is 6. 6, the next is 7. 7, the next is 8. 8, 9, 10, 11. Oops. 12, 13, 14, 15. Okay, so 8 should next go to 9. 9 should go to 10. 10 should go back to 0. That's the definition of a modulo counter. The rest of these are undefined. There is no 11, 12, 13, 14, 15. Okay? But I've got more than enough stuff. I am going to currently just make these all zeros. Just restart my counter. That's not 8, so those are zeros. So this is my modulo counter with the unused things down here, right? Because 10 goes to 0 is legit part of the counter. But this part down here is unused, which is states 11, 12, 13, 14, and 15. Is that good? Yes. Okay. So when we take this, right, we're going to take this. I'm going to do a simple mux design. Right? That's why I've kind of branched them off 2 at a time. So let me do them one mux at a time. So this will be for my most significant bit. So that's this column right here. That's my most significant bit. Mux design says you take the first 3. So that's my current states. I've got a 4-bit parallel load. D3, D2, D1, D0. Because this is 3, 2, 1, and 0 in my positioning. So if we were to implement this in Verilog, you would just go 3 down to 0. This is 3, that one is 0, bit naming wise. I'm going to do the first column, current to next. So I'm doing the one that's going to do D3. Does that make sense? Yes. Okay. So Mux design, the output of this, I'm doing this a little bigger. I have Q3, Q2, Q1, Q0. The most significant 3 bits, that's these, are the same for any of these kind of blocked out sections. That becomes the controller for all of my muxes. Every one of my muxes is going to use those most significant bits. And then the pattern in here will either be 0, 0, in which case it means give it a 0. It'll be a 1, 1, in which case we give it a 1. Or it'll be something like a 0, 1, in which case I give it the least significance, the same as Q0. Right? 0, 1, 0, 1. So if it's a 0, 1, I give it Q0. This is just your regular mux design. 0, 1, 2, 3, 4, 5, 6, 7. That's what 3 bits, and that's what I was given. Right. So I just walk through 0, 0. I get a 0. 0, 0. I get a 0. 0, 0. I get a 0. 0, 1. Right? This is on number 3. I get a Q0. Just to keep my thing from getting ugly, I'm just going to write Q0. I get a 1, 1. I get a 1. And all the other ones are all 0 because they're unused states. So far, so good. So that's my first of my muxes that has 8 inputs. Okay. I promise I'll finish this up quick as long as I know people are following me. Is my volume still on? We're good? Yes, okay. So then I want to go to the next column. So I'm no longer doing the most significant. I'm now going to do the second most significant. Column number 2 in my next. That means I'm not doing D3. I'm now doing D2. So I'm now on a second one of these. Remember, I got 4 of them. First one went to D3. So that one's done. The next one is going to go to D2. So if I were drawing this as a picture, I'd need one up above and one here and one below going to D1 and a final one below that going to D0. There'd be a total of 4 of these, each one of them outputting to one of these. We did the topmost. My whiteboard ain't that big. I have to do them one at a time. So this was the previous, or maybe I should say the first one we did. That goes to the first mux. We're going to do the second mux, walking through the same way. 0, 0, I get a 0. 0, 1, that's the same as Q0. I put a Q0. 1, 1, that's a 1. 1, 0, that is identical to Q0 primed. If you look in the description of the problem, I said I also gave you an inverter. Then I have a 0, 0, and everything else is zeros. So I can just zero everything else down. And that does the second column. Good with the second column? The mux design is really nice for building these, right? This is a very fast counter. The only thing it requires is a fairly big mux, but not too bad. Okay. Looks like we've got people saying yes. Then I do the next column. Which is the one that goes to D1. That's this column. Its output goes to D1, but uses the same addressing, and it'll still be 0, 1, either Q0 or Q0 prime as the inputs. So I just walk through, it's a 0, 1, same as Q0. And then it's a 1, 0, that's Q0 prime. We already have that because we have the inverter. I get another 0, 1, that's Q0. Then I get a 1, 0, that's Q0 prime. And then I get a 0, 1, that's Q0. And then everything else is zeros. That's D1. Right. And D3 still got the first mux. D2 is the second mux we designed. Now we've done our third mux. So all that's left is this last column. So we'll now do the last or the fourth mux. Right. So it goes to D0. It's just this last column. The last column, it goes 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. It's always the same for the first 5, right? 0, 1, 2, 3, 4. The first 5 of them is always 1, 0, which is Q0 prime. want to do this really fast and easy because I don't feel like writing them all. And then everything else is 0. That's the least significant bit. And I am done number 3. So remember, Mux design is really easy. So I gave this Mux one here actually to try to be nice and to make it quick. But it also is a way for me, without having to add an extra problem, that I can test something from the first half of the course. Do you remember Mux design? Mux design is fast and easy to do a lot of these. We have not done a counter with Mux design yet. We have used Muxes, but we didn't do regular Mux design. If you remember early on, I told you Muxes are our friends. So when you get Muxes, right, you should be like happy. And my inputs were half the size of the number of states, right? And so I need to be able to have 4 different possibilities for each one. Mux design does that. So Mux design should jump to your mind on that one. Does problem 3 make sense? When do you get a 1 instead of Q0 or Q0 prime? When both of the numbers are 1s. So if you look right here, I've got 2 1s. They're both 1s. So in that one, I put a 1 there. Here in this this column, I had 2 1s together. So I put a 1 as an input for that one as well. So if they're both 1s, I put a 1. If they're both 0, I put a 0. If the pattern is 0, 1, which is the same as the least significant bit of my current, Q0, then I put Q0. If it's the opposite, like this, 1, 0, it's the opposite of 0, 1, I get Q0 prime. Good? All right, we're technically at 2, which is out of time. So the 4th problem is a challenge problem. It doesn't actually count against you on this. This is just a way to get extra credit. I'm more than happy to explain how this one works, but we're also at time. So I'll give you 2 possibilities of how to do this. I can stop this now, record a video, and upload a video for that one. I can continue recording this one, and whoever needs to leave can leave, and you can jump back to whatever count it is inside the recording. You can submit corrections to the homework except for the challenge problem, because the challenge problem is not technically part of the homework. It was a way to get extra credit for the final. And so for that one, since those are free points, it literally doesn't cost you anything. I don't think it's quite fair to do that one as freebie points when I'm going to explain it. If people want to do the challenge, there's no easy way to do that. So I think you did the. Was anybody able to think they got the challenge problem number 4? Okay. So I'll give you this option. Do you think you could do the challenge problem now? Some yeses, some not sure, stuff like that. Okay, how about this? I won't cover the challenge problem now. I will give you through tomorrow night to try to tackle the challenge problem. And I will upload a video explaining the challenge problem on Saturday, when I also upload the practice tests. Is that fair? Thank you. I'm always happy to get blessings. Okay, so we will stop at this point. I will not describe the challenge problem. Let me give you a hint towards the challenge problem. Okay? the hint towards the challenge problem, if you notice it's smaller, right? I halved these. But so since it's halved, you have to have more options inside these. So you have to be able to rearrange them. And the trick towards this problem is these ones that are all 0 down here, make them X's. So they become don't cares. This is the first thing. I'm sorry. 10 goes to 0. That doesn't change. That always has to go to 0. But the 11, 12, 13, 14, and 15, you have to make them X's. You can't do it without making them X's. And now you need to group these in a slightly different way so these X's get distributed around. The way you can group things so that they get distributed around, I'm going to erase this. Since you want one of these in every one of the sets, if you kind of look at these, you've got groups of 4 because it's a 4-input mux, which means you're going to be making groups of 4. If I use the most significant bits, you'd be grouping them like this. That doesn't really help you, right? But if you renumber them, if you notice 0, 1, 2, 3, right? 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So there's a group of X's where the least significant has 0, 0, and 0, 1, and 1, 0, and 1, 1. So if you renumber this so that you have the 2 least significant bits, so you have Q1 and Q0 in the most significant bit spot. And you have Q3 and Q2, what is the most significant bits in the least significant bit spot. This will all of a sudden become doable. That means for these two 0, I've got the possible patterns here 0, 0, 0, 1, 1, 0, 1, 1. 0, 1, and these will run through. So I'm reordering, right? Flipping their order. So now I have to redo these. I take least significant bit 0, 0, most 0, 0. So this one still goes here, right? And then I can write them in, right? I'm going to flip the order of the other bits too. 0, 1, 0. Taking the second half in the first, and the first in the second. 0, 0, 0, 1, 0, 0, 0, 1. Remember? 0, 0, 0, 1. They flip their order. Right? So 0, 0, 0, 1 is this line. 0, 1, 0, 1. 0, 0, 1, 0. Flipping the order is 0, 0, 1, 0. And I get 0, 1, 1, 0. And then 0, 0, 1, 1, 0, 0, 1, 1 is just X's. Now I have an X. And every time I hit the 1, 1s for all of them, right, most significant bit 1, 1s, they're all going to be X's. That makes sense for the reordering. Right. You should be able to walk through and get the rest of them, right? 0, 1, that's this one, this one, this one, and that one, which you've already labeled. Right? So 0, 0, right? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Well, we already did all the 1 1s. Right? You can fill these back in. Just remember to flip these orders when you write them in. Right? Then you'll have something with X's in them. Right? You've now used Q1 and Q0 for your 4-bit muxes as the addressing. Then you've got Q3 and Q2. Right? And when you look at the patterns in here, 0, 0, 0, something. What could I put into the mux at input 0 that would give me all zeros? And then whatever I want to choose. All ones and what I want to choose. 0, 0, 1, something. Is there something over here that I haven't used that looks like 0, 0, 1, something? Right? 0, 1, 0, something. Anything here that looks like 0, 1, 0, something. Right? You ought to be able to figure out inputs I can put from Q3, Q2, 0, and 1, and possibly their primes. Right? And so you've got 2 NOT gates which allow you to deal with Q2 and Q3. And you can use either Q2 or Q3 to be patterns now. Right? And these X's will give you enough flexibility that you don't have to deal with any of the weird cases. Right? So that's a pretty big hint. So if you use this, you have a decent likelihood of being able to fill out the rest of the table and therefore fill in my mux design for me. All right. Hopefully that helps. Again, if you're not able to do it, I'll give you a separate upload. If you do it, great. If you get part way, we'll give you some partial credit. It's just a way to have a couple points sitting in your back pocket coming into the final. I will also give you practice exams with solutions. Make sure you let me know when you're available, not available. Maybe I'll put a discussion board up to have people put up those things. And really the best thing is tell me when you're not available, when you honestly really can't do it. It's usually very hard to meet these. So if you just tell me when it doesn't work. So for the corrections for the test part, I'll give you an extra credit uplink. As soon as I'm done here, I will log in and make the extra credit, which is the fix for the test part. And then I'll also make an upload one for the challenge problem, which I'll just call challenge problem. I'll probably put that down under the final section. And I'll make that one close Friday just before midnight. Okay, we good? So be watching. I will need your date and time things that are available, so I make sure I pick a good time for the practice section when we can work problems like this, but that you get to pick. And watch for the practice exams. I'll probably put one on Saturday, give you a little time to process that, and then do another one on Monday, give you a little bit of time to do that, so it kind of spreads them out. All right. Well, if everybody's good, I wish you a good weekend. Hope everything is going well. Stay safe. God bless you all. You too.